All right, so in this picture, we can see a girl running from left to right. The rain is coming down vertically. And let's talk about frame of reference. So what is the velocity of the rain in respect to the girl? So go ahead and pause the clip and draw that out. And yeah, let's see what you come up with there. All right, so you should get the combination of the two. So with the girl as the frame of reference, the rain is coming down, at an angle. And so, we've talked about our classroom, our classroom being still through, our study. And, but in reference to the sun, we're definitely not, right? Because the sun, the earth is going around the sun, and also the earth is rotating. And so, yeah, we're definitely moving relative to the sun. So we always have to talk about the frame of reference before we can really talk any more about motion. Remember with distance and displacement, right? So distance, just how far. Displacement, in this case here from A to B, how far is 100 meters. Displacement, 50 meters, but we'd have to say direction. So in the positive y-axis, or if this is north, south, east, west, 50 meters north. Now on your equation sheet, you're not given these equations. They expect you to know, what speed is, distance in a period of time, and what displacement is, or velocity is, which is displacement in a period of time. All right, so from this graph, go ahead and determine the average velocity. So go ahead and pause the clip, and when you're ready to check, you can hit play to continue. All right, so you should get positive 0.33 meters per second. We've got our rise or our run. How about instantaneous velocity, 1 second? Go ahead and pause the clip and give this a try. When you're ready to check, you can hit play to continue. All right, so you should get the tangent line, our rise, and then our run, and so something around 2/3 meters per second. Go ahead and describe the motion of this particle. So go ahead and pause the clip and describe what, if this was the graph that we're given for the velocity and time, what that would be. All right, so we should get, for that last one, a positive constant velocity. How about for this one? Go ahead and pause the clip and give this a try. And when you're ready to check, you can hit play. All right, so the velocity in this one is 0 meters per second. And then for this one, go ahead and describe the motion of this particle. So pause the clip, and when you're ready to check, you can hit play. Okay, so for that last one, positive constant acceleration. If we get the slope of that, we get the acceleration. It's getting faster and faster on the last one, starting from rest. All right, so for this one, go ahead and determine the acceleration from the graph, and then secondly, go ahead and describe the motion. So go ahead and pause the clip and do that, and when you're ready to check, you can hit play to continue. All right, so for this one, again, get the slope. The rise in this case would be positive 30 minus negative 20, so 50 over 5 seconds. If you did a smaller portion of the graph, that's fine too. And then what's happening here with the motion, it's starting out with a negative velocity. So if this object's starting out going this way and then getting slower, coming to a stop, and then it's getting faster and faster and faster this way. Okay. All right, so for these graphs, go ahead and draw what they would look like for a stationary object for the position time, velocity time, acceleration time. So go ahead and pause the clip and give this a try, and when you're ready to check, you can hit play to continue. All right, so position time, still, just staying at the same position. 0 velocity, and the acceleration is also 0. The velocity is not changing. Or we could be standing in the negative, a negative displacement. All right, so go ahead and do that for this one here. The graphs for constant non-zero velocity. So go ahead and pause the clip and give this a try. And when you're ready to check, you can hit play to continue. All right, so in this one, you get a constant slope for the position and time. And if we get the slope of that, we get velocity. Constant positive velocity here for that. And the acceleration is 0. The velocity is not changing. If we're going backwards at a constant velocity, it'd be like this. We get a negative slope, a negative velocity, still no acceleration. All right, and how about for this one, for a constant non-zero acceleration? Go ahead and pause the clip and give this a try. When you're ready to check, you can hit play to continue. All right, so remember, with position time graphs, they're going to be curvy if they are, constant non-zero acceleration. In this case, positive acceleration. So the velocity could be starting from rest or some value, and so we get a constant slope. And if we got the slope of that, we would get the velocity, or the acceleration rather, which in this case would be a positive velocity, or positive acceleration rather. Now this could be all negative, right? We could have a negative acceleration, and then the velocity is getting faster and faster in the negative, therefore a negative acceleration. All right, so use your current equation sheet with the this 2.1 on your equation sheet as the section. They give you the kinematic equations. And yeah, go ahead and try this constant acceleration situation here. Draw it out, work out your values, and then when you're ready to check, you can hit play. So go ahead and pause the clip and give it a try, and then hit play when you're ready to check. All right, so you should get negative 11.267 meters per second squared for the acceleration. The velocity final should be 0. The initial is 130. And you only have 3/4 of the runway available, so we're dealing with 750 meters as our displacement. All right, so how about for this one? We drop a ball from rest off a 120-meter high cliff. Assuming air resistance is negligible, A, how long is the ball in the air? And then B, what is the ball's speed and velocity when it strikes the ground? So go ahead and pause the clip and do this one. When you're ready to check, you can hit play to continue. All right, so for this one, the displacement is negative 120, and we should get a time of 4.95 seconds. And then when it hits the ground, we should get a speed of 48.497 meters per second, which then would be, for velocity, it would be 48.497 meters per second downward. All right, and then for this one, what is the speed and ball speed and velocity when it's reached halfway? And then D, draw the graphs for position time, velocity time, and acceleration in time. So go ahead and pause the clip, and when you're ready to check, you can hit play to continue. All right, so halfway should be 34.3 downward, and then our position and time, we're starting at 120 meters and then falling down. This is exponentially going downwards, and should be, right? It's an accelerating situation, so it's going to be curvy. Velocity time starts at rest, and then it's getting faster and faster in the negative, and then the acceleration is negative 9.8. All right, so now we're going to talk about fluid resistance. When an object goes through a fluid, there's a resistant force against the motion, and we can get that by calculating using these equations. K is the resistive constant, which is how much the fluid is affecting it. So the density of the fluid, how much surface area you have for the object that's trying to go through. For higher speeds, you're dealing with kV squared, and so it becomes more exponential as you get into the faster speeds. And then V is the speed of the object itself through the fluid. All right, so yeah, let's go ahead and consider this. Go ahead and draw. This is assuming that the object has no air resistance. Go ahead and draw what the graph or what the ball would look like if there was air resistance. And so go ahead and pause the clip and give that a try. When you're ready to check, you can hit play to continue. All right, so for this, we should have it should be shorter, and it shouldn't go as high. And so that's what we're dealing with there. Terminal speed, that is where the air resistance becomes so great with that higher speed that it balances out the weight. And eventually those will match. The weight will match the air resistance. And so what I want you to try is to derive the equation for terminal speed. And so we have force equals kV. So go ahead and drive the equation for terminal speed. And when ready to check, you can hit play to continue. All right, so the weight is mg, and the terminal speed then is taking the weight divided by k. And that is, yeah, that's our terminal speed. So let's go ahead and try a Sample problem here, the force of air resistance based on the data given is F equals 0.653 V. What is the terminal velocity of the 3 kilogram object? So go ahead and pause the clip, give this a try, and when you're ready to check, you can hit play to continue. All right, so we should get terminal velocity of 45.02. So at that point, the weight is going to equal the force of air resistance.